Hey guys, welcome back to Simply AI. In our previous videos, we have learned about the linear regression and its practical implementations using Python. And today, we are going to take a different angle and explore linear regression from a probability point of view. Before we dive into the probabilistic approach, let's quickly recap what we have learned so far. First thing we learned that how linear regression is a fundamental technique for modeling relationship between variables. Secondly, we learned about terms like hypothesis and loss function. And at the end, we learned how to use gradient descent algorithm to minimize our loss function. Basically, our focus was on minimizing the difference between predicted values and actual data points. And we used best fit line approach in order to do so. If you haven't had the chance to watch those videos, I will provide links to the videos in the description. I know you have seen these equations and code before in our earlier videos where we have already discussed them in depth. And primary question was in our previous approach was why did we choose a squared loss function? Why was this specific function chosen over others, right? And in this video, we will get the answers. Other than this, we will be able to think about any machine learning problem from a probabilistic perspective. So let's quickly move on to basics and understand what is meant by probability. You have a bag of colorful marbles, red, blue, and green. Let's say you want to know the chance of picking a red marble from the bag. Okay, that chance is called probability. It's like asking what are the odds of getting a red marble, right? So the probability, you will say it will be the number of favorable outcomes upon the number of total events. And this is how we represent it. So here probability of A, or we say the probability of getting red marble will be 1 by 3 because there are three balls and there is only one red ball. So number of favorable outcomes is 1 and the number of total event are the 3. So we'll say the 1 by 3 is the probability of getting red ball picked. So let's talk about the conditional probability. So imagine you have two bags of marble. It's like you have two bags, like bag A and bag B. Bag A has more red marbles and bag B has more blue marbles. You want to know the chance of picking a green marble from bag A. But wait, first you have to pick a bag, right? So once you can pick the bag, then only you can pick a marble. So depending on which bag you pick, the chance of getting a green marble changes because the bag A has more red marbles, and if you're picking bag A, chance of getting green marble is less here, or chance of getting blue marble is less here because the bag A has more red marbles. So that is the conditional probability. So it's like asking what are the odds of getting a green marble considering which bag I have picked. So if you will say like if A and B are two events in a sample space S, then conditional probability of A given B is defined as probability of A given B equals to probability A intersection B into probability of B. Okay, and this is how we represent it. So probability is about the chance of something happening, and conditional probability is when that chance depends on something else happening first. Just like picking marble from different bag changes the chances of getting certain colors. Okay, so let's move on to the new term, which is Bayes' theorem and conditional probability. So conditional probability is the likelihood of an outcome occurring based on a previous outcome having occurred in similar circumstances. Bayes' theorem provides a way to revise existing prediction or theories given new additional evidence. And we are going to learn about this more into when we use the Bayes' theorem in order to predict few values. So this is how we represent the Bayes' theorem, where the probability of A given B is equal to probability of B given A. When I'm saying given A, that means like B is happening after A. So it's kind of B is dependent on A into probability of A upon probability of B. So PA is here, probability of A, and all this, you can break it out. Another important term in probability is distribution. A probability distribution is like a special math rule, and that rule tells us how likely different things can happen in an experiment. It helps us understand the chances of different events taking place by using numbers and a way to figure out the possibilities. Okay, so the number of times value occurs in a sample is determined by its probability of occurrence. And there are so many, maths function or probability math functions, and these functions are here. So right now, if you don't understand these functions, you do not need to worry. Okay, and for now, we are mainly going to use normal distribution and binomial distributions. And once we will study the normal and binomial distributions, we will learn more about those things. So basically, we will not go deep into it. Instead, I will create one separate video where we can learn about probability concepts in more detail. So let's quickly move on to today's agenda and try to think about linear regression problem from probabilistic point of view. Okay, so I think we are now familiar with this symbol where it means that we want to calculate probability of y on given x. So it's like, the first x is happening and then we want to calculate the y. And the new thing is x semicolon theta. So we will read as a, that x is parameterized by theta. But probability is not dependent on theta, or it's not going to affect anything. So it's just that whatever the x equation will be, it will be, you know, like there will be a theta in that equation. So we read this thing as a distribution of y given x parameterized by theta. So instead of the probability, we will consider this as a distribution. So we have already discussed about the normal distribution, binomial distribution. So here, this is just a representation of distribution. Now let's move on to the definition of the distributions. So it's just a a function, or you can say it's a math function that describe all the possible values and likelihood that a random variables can take within a given range. So you have few values, and then from those values you find out your distributions, and that distribution is going to be true for others value also. So it's like you can generate more input and output using your existing input and output value. If it does not make sense, we are going to discuss about this later in this video. So before starting, we are going to make few assumptions, and this is the one of them. So let us assume that the target variables and the inputs are related via these equations. And if you will see this equation, it's kind of looks like a linear y equal to mx plus c. But here, this equation is a completely different. It's not a linear equation. Here, if you will say the eta of I is an error terms, and that captures either unmodeled effects, such as if there are some features which we did not consider, like floor area, or it could be anything, and we call this as a random noise. So the eta I is a noise, and we need to assume that this random noise, since we don't know about these features, we are going to assume that this random noise is distributed like a normal distribution. So for this random noise, we are going to consider our distribution function is normal distributions, and we call it as a Gaussian distribution also. So both are the same. So when we talk about the Gaussian distribution or normal distributions, both are exactly the same. If you remember, previously we discussed this is our normal distribution function, right? 1 by root 2 sigma exponential of eta I square upon 2 sigma square, and here sigma is the variance. So one thing which we are considering here, we are considering mean as 0. So if you will go and look at the equation, yeah, so you can see the normal equation here is the x minus mu square, and mu is the mean and sigma is the variance. So x minus mu square, and since we are assuming that the mean is 0, it's going to be x square, and x is what, eta I, right? So this is going to give us, so this is going to give us this thing. So probability of eta I, or we can say the distribution of eta I, is equal to normal distribution where the mean is 0. Okay, it's very simple. Now, uh, we have the another kind of representations, and we can represent this thing like this also. And this is the normal distribution notation. We use this notation to pass our mean and the variance. So the first parameter is going to be mean, and right now it's a 0, and the second parameter is a variance, which is sigma square. So since our eta is yi minus theta transpose xi, here we assume that our yi is theta transpose xi plus eta I. So eta I will be y minus theta transpose x, right? And this looks like, we are comparing our actual value minus predicted value. So here I'm just, trying to uh, here I'm just trying to show you the pictures with respect to linear regression, which we have previously done, but it's completely different approach. So we are just saying that our eta I, which is our random noise, is yi minus theta transpose xi. So noise, you can see, whatever the difference you are getting from predicted value and the actual value is the noise, right? And your target is to minimize the noise, and this is what it is. And your noise, the probability of noise has, the normal distribution. So it's kind of making sense. So we have a noise, and noise is nothing, it's just a difference between predicted value and the actual value. And what we are doing, we have one distribution function. We are assuming that it's normally distributed. So probability of eta I is going to be this. Now, this implies that the probability of y given x parameterized by theta is going to be this, correct? And we can represent. So if you will see again, and if you will compare this with our normal distribution function, here it was y minus mu square, right? So mu was the mean, and here in place of mu, theta transpose x is there, right? So we will say that theta transpose x is the mean, and the sigma square is the variance. So we can represent this yi, like yi given xi parameterized by theta is equal to normal distribution of theta transpose xi comma sigma square, where the first parameter is a mean and second parameter is a variance. So the probability of the data is given by, probability of yx theta. This quantity is typically viewed a function of y for a fixed value of theta. So this thing is the function of y and x, and theta is a fixed value, right? So instead of considering this thing, what we are going to say that, hey, y and x are fixed value, and theta can be anything, or theta is a variable. So instead of considering this as a y and x function, we are going to consider it as a theta function. And once we will do that, we will call this function as a likelihood function. So you will heard this likelihood terms so often in machine learning and in deep learning. So what does mean by likelihood function? It's very simple. So whatever the distribution of your distribution of your noise is, right? And if you will consider that same distribution as a function of parameter instead of considering function of y and x, then whatever the result will be, that will be your likelihood function. So we represent this likelihood of theta, or we can say it's the function we are considering that is a function of theta, and it will be like this, that likelihood of theta on given x and y. It will be equal to probability of phi on given x parameterized by theta. So it is just a representation of likelihood function. Since initially we assume that eta of I is the independent, right? So the one, so suppose if there is one data set and we calculated the random noise for that data, and then the random noise for another data. So both noise are independent. And since both noise are independent, the probability of both noise will be also independent. And likelihood function is going to multiply that. So suppose if we have n number of set, we are going to multiply the probability of y given x parameterized by theta. And the pi is the just a representation of multiplication. So the way sigma is the representation of plus, the pi is the representation of multiplication. Okay, so we can see, or we can say that our likelihood function is going to fit this, and if we will write this as a normal distribution, we can write it as this. So now given this probabilistic model relating yi and xi, what is the reasonable way of choosing our best guess of parameter theta? So that is our task. Like, how can we choose theta. So the principle of maximum likelihood, because we want to maximize the probability, right? So the principle of maximum likelihood says that we should choose theta so as to make the data as high probability as possible. We should choose theta to maximize likelihood function. And that is what our next task is. So in our previous approach, we had the loss function, and our task was to minimize our loss function. But here, we have taken the probabilistic point of view, and here, whatever the distribution we have written, we want to find out the theta which will maximize the probability. Correct? So that is what our task is. Let's see how do we do this. So the first thing, because this function looks like a complex function, so instead of maximizing the likelihood, we are going to maximize the log likelihood, which is nothing, just the log of your likelihood function. So we represent this as a small case L theta and equals to log large case L theta. So this is the just a representation of this. So we want to maximize log likelihood. So this is the just a simple mathematical explanation of this. You can just go line by line. So I think the first term is very clear, right? It is we have just replaced likelihood function to our normal distribution function. And since we are taking the log, and this is the pi, which means we are doing the multiplication. And once log will go inside that pi, it will convert that multiplication to plus, right? And it will convert into sigma. So sigma of log these terms, and again, these two terms are multiplication, right? The 1 by root 2 pi sigma multiply e to the power that term. So again, since this is a multiplication, this is going to be a plus sign, and since there is a minus, the minus will come out, and this will be our final term. So now if you will see, the first term is the n log 1 by root 2 pi sigma, and the second term is this. And our task is to maximize this L theta. So since we are doing minus operation here, and 1 by root 2 pi sigma, everything is a static, right? There is no variable. So the only way this L theta can be maximized is we will minimize the second term. So 1 by sigma square into 1 by 2, and this term we want to minimize it. And if you will see this term, the only part we can minimize is yi minus theta transpose x whole square. Okay, so now our task is to minimize this term, because if we will minimize this term, we will maximize the log likelihood, and if we will maximize the log likelihood, it will maximize the likelihood function, and that is what our task is. Correct? So now look at this function, right? This looks like our squared loss function from linear regression. So when we saw this thing from the probabilistic point of view, we got the same function which we considered initially as our loss function. So our biggest question was, why are we calculating a squared loss, correct? Why are we taking a square? So I think now you guys got the answers. Since we consider our random noise as a constant distribution, at the end we got this function which is nothing but a squared loss function. So that is the reason we used a squared loss in our linear regression. So that is what our task is going to be, like identify the problem and then choose the probability distribution as per that problem. And then get your likelihood function. Likelihood function is nothing, it is just a distribution function. But instead of looking at the function of yx, we will look at a function of parameter. In this case, it was theta. So get your likelihood function and then maximize the log likelihood, because if you will maximize the log likelihood, you will maximize the likelihood function. So maximize the log likelihood and then use gradient descent to minimize the component. So when I'm talking about the component, that means this is the component, right? And if you want to maximize the log likelihood, you want to minimize the component. And again, it's the same problem, I think, which we have already learned. If you want to minimize this thing, we will use gradient descent to minimize what we have already learned. Okay, so initially we made few assumptions, like our mean should be 0, and about variance, and about our uh, function which was like linear regression line. But we need not to make those assumptions, and we can you know still use the probabilistic approach without having any assumption. So in our next videos we will talk about this, and we will try to implement probabilistic approach without having any kind of assumption. So as we wrap up today's video, you know how to think about machine learning problem from probability point of view, and you know why did we use squared loss, right? In next video, we will talk about this more and try to implement classification using our probabilistic approach. So when I'm talking about the classification, it will be, you know, variety of problems like classified whether it's a cat or dog and classify the disease and those set of problem we are going to address in our next video. So if you like this video, don't forget to like, share, and subscribe for more exciting content. And remember, the world of machine learning is full of exciting twists and turns. So stay curious, keep learning, and we will catch you in the next video. Happy exploring. Thank you.